speeding up computation, mostly geared towards R. Really the point of this is that there's tons of things that I've learned over the years that nobody told me, and it's kind of hard to find, and just my endless scouring of the internet while procrastinating from doing my work has led me to some of these things. And it's helped my computation tremendously. And so I'm going to go over 3 parts of this: hardware considerations, just because I know a lot more now than I've built computers in the past, and didn't really know everything I should have when choosing hardware. And hardware has actually been speeding up in how good it's getting recently in the past 8 years or so. I'm going to talk about BLAST libraries, which is the easy way to speed up R that just everyone should do if you're using R. And then calling C from R is really more advanced R programming and taking advantage of really what the language provides you with. And so to start, before we get into anything, this is why I love R. But really any interpretive interactive language has these benefits. It's extremely quick to develop a program in it. The fact that you can step through each line of a loop, see exactly what the output's going to be, change things on the fly, just makes interactive languages very quick to develop. But all of them, even the fastest of them, are going to sacrifice speed compared to the classic low-level languages like C and Fortran. And it just has to be that. Even when the just-in-time compilers like Julia do help a lot for some naive programming, but you're always competing against C or Fortran. But you still would like your interpretive interactive language to be as quick as possible, because when I'm debugging code, I don't want to have to wait 30 minutes for each run. I'd much rather wait 5 minutes to see if there's errors or if my output looks strange and I need to change something. So really how I view R programming is you really should view it as modular. And you write your R algorithm, make sure everything's working correctly, and then you can start swapping out portions of it to speed things up. So I'm a Bayesian, so when I do my MCMC, I do all my loops in R. Once I know that the chain is moving correctly, I need to do a final run with, say, millions of steps. That's when I then swap out that loop for a loop in C and run the final one. And so the reason why I like staying in R, I have done some things, just programs written entirely in C, but R just has excellent graphical abilities and the ability to bring the output of my MCMC directly into R, interface it, and then have my entire program produce all of my fancy plots and whatnot to put in papers is what I really enjoy, not having to mix languages really, or mix them in terms of separate programs. And the user contributed packages on CRAN are just, some of them are excellent, and I wouldn't want to have to give that up, especially when needing to compare to competitors' method or something like that. Okay, and so now to start really the ways that we can speed up our programming. Now this applies to any language, any program you're doing. The most straightforward way is just to get faster hardware. And hardware is progressing fairly quickly. But when you read reviews of things, the thing that drives me nuts is you read a review of a processor or video card, something like that. All anyone cares about is how many frames per second they get in whatever game they play. And I don't play games, so this is all just meaningless to me. I have no idea what they're talking about. I don't know what these games are. All I care about is how fast my programs are going to run, how fast I'm going to be able to analyze data. And so something that is an important kind of theoretical property of processors is the number of floating point operations they can do per second. One thing, some people, I put the S in flops for the plural of operations. Some people mean that S to really mean the per second, so this might look strange to some people. But floating point operations per second is really the key when you're doing statistical or scientific computing. And this can be very different than the number of just instructions per second that a processor can do. Because for a long time, floating point operations have actually been run on a separate component to the main core of the processor. And so when you're considering hardware, the thing you really want to look into is this theoretical peak flops per second. And you're never going to get to the peak, but it's useful for comparing hardware, and you can have some idea of the percentage of this peak that you can get to. Now, I mentioned both single and double precision. R only works on double precision, so that's something to consider. Julia, I know, is better at letting you actually choose what types of variables you use. And in R, you could do things in the background in single precision and convert over, but that adds a little bit of time. So to talk about CPUs, Intel and AMD are the two big competitors, and they're very, very different. So one thing that's important to know is when AMD advertises cores, they're really talking about, you can think of them as integer cores. But these cores are paired in what they call modules, and each module only has one floating point unit. So if you're doing nothing but floating point operations on an AMD processor and you have an 8-core AMD, it's really acting like a 4-core processor. Now some things, if you're doing, just say, random integer generation, the integer operations, you will see a speed up in that doubling of cores to the 8-core. But in a lot of things, you won't see any difference moving from 4 to 8. For Intel, their cores, a physical core, are completely independent. Now, Intel has a thing called hyperthreading, which allows 2 threads to use the same physical core, and it switches very quickly back and forth between them. If you're doing similar operations, that will slow you down. And on the older generations of Intel, it can slow you down 20% or so. Hyperthreading has got much better, or some people leave it on. When I've done code where I run very long programs in parallel, hyperthreading can be good. If there's a potential that they're doing very different things at different times, it can speed you up. But for things like matrix-matrix multiplication, if you're using all the cores on your machine to do matrix multiplication, it'll definitely slow you down. And so the main thing to take into consideration if you're debating between processors is that they have very different flops per cycle characteristics. The new Intel Haswells can do 16 double precision floating point operations per second, and this is a property of most all CPUs. They can do twice as many single precision flops per cycle. AMD has been, this Bulldozer has been out for a few years, and their newest iterations of their cores still do 8 double precision flops per cycle. So 2 examples just to show you how naive just looking at hardware can be very misleading. 6-core Haswell processor running it, this isn't its base, its standard clock speed, but can easily run at 4 gigahertz. 6-core Haswell running at 4 gigahertz has a theoretical peak of 384 double precision gigaflops per second. So now moving, it would be too many zeros to look nice. Whereas an 8-core Bulldozer AMD processor running at the same clock speed is going to have a theoretical peak of only 128. So it's 3 times slower than the Haswell, even though it has 2 more cores. And so this is just something to keep in mind when you're looking at what hardware you might consider. And so one thing to note is that the theoretical peak can be much higher than actual peak performance, especially in small problems. And now talking about GPUs. One thing I do want to mention about CPUs before I move on, some of the stuff we're talking about, if you're really taking advantage of everything a processor can do, can make processors run very, very hot. Especially the ability of Intel to do these 16 double precision flops per second. They've added instructions to their processors, which actually ask for more voltage from the computer, which makes them even hotter. So if you're going to be running things for hours or so and taking advantage of all of your cores, you probably don't want to do it on your very fancy, expensive laptop that doesn't have a good fan to cool things, because you have the potential to fry it. So that's always something to keep in mind. So now talking about GPU hardware. GPU hardware is a little bit different. The 2 main competitors for that, AMD bought a previous competitor, I think ATI was the old name. So AMD and NVIDIA are the 2 big GPU manufacturers. And the thing to note about these when you look at that hardware is in general they don't have the 2-to-1 ratio of single to double precision performance. And a lot of times they can have this, but these companies sometimes purposefully cripple their hardware. for two reasons. First of all, for gaming, single precision performance is really all that matters. Games don't use double precision because they'd much rather have the faster rate of single precision, and for putting pixels on a screen, it doesn't matter if you have that double precision to do that. Small errors are tolerated. But there are a couple consumer line cards which can really get to the workstation line performance that these companies offer. And so for what I know, there are some, I say single chip because there are some video cards that actually have two chips on a single board, and that's the equivalent of using multiple cards, but there's some trade-offs to having it on one board versus a single board. So to give you an idea, this card is now out of production. There's a new one which doesn't have the same double precision performance, but this card has a theoretical peak of 1700 double precision gigaflops per second, which is just huge compared to these CPU numbers. But the one thing to consider is, why not move up to one of these workstation cards? Well, that's, if I want to use Titan, this shouldn't say Tesla. Tesla's the workstation line. If I want to use Titan Black, I can get one maybe for $500. If I want to use the equivalent is the Tesla K20, I'm looking at $2,000, $2,500. The main difference is this ECC RAM, which is error correcting code RAM. And that RAM has errors, random errors that pop up. Things will get flipped, zeros will get flipped to one randomly, and this ECC RAM can catch that and correct it. And so if you're doing something like sending people to Mars or something where people might, bad things happen to them if you have an error, you probably don't want to be running things on your desktop at home. Probably want to be using this kind of error correcting RAM. But for me being a statistician with toy data sets, not having this is fine. And the code that I develop, if someone implements it on a server grade machine, it'll still run. There's no consideration you have to make in your code for this kind of RAM. So between these two competitors, NVIDIA is much more popular in the supercomputing world. If you look at the top 500 supercomputers and look at the ones that use accelerators, the NVIDIA cards are much more useful. There's Oak Ridge National Labs has, I think their supercomputer is called Titan, and they use nothing but these NVIDIA cards. And the CPUs are just used to throw jobs to those. But there's two kind of different libraries that you'll use. AMD really uses OpenCL, which is much more general. AMD and Intel are both moving to having GPUs on the same chip as a CPU in their low, mid-level lines of processors so that people don't need a separate video card to use their computer. And so this OpenCL can, AMD calls their new CPUs with those properties APUs, and OpenCL really views those all as the same devices, whether it's a CPU or a GPU on the same chip or not. NVIDIA has this Cuda library. It's a Cuda Toolkit, which you can download online, and that's very proprietary. It won't run if you put an AMD GPU in your computer. It's not going to be able to use that. But the Cuda libraries are much more well developed and much more widely used, and so this is what I prefer. If there's never been a problem I've had that I can't fix by searching Google and having someone else had the same problem and tell me how to fix it, which is what I like. And so one thing to notice looking at those theoretical peak performance is that if you want just as many flops per second as you can get, it's much less expensive to go with GPUs and CPUs. To get something with 1,000 gigaflops per second in a CPU, you're probably looking at spending $3,000 versus a couple $100 to get it in the GPU. And now some of these libraries, especially in Cuda, can take advantage of multiple GPUs. And this CU Blast XT is the newest one in the Cuda Toolkit, and it's now included in the Cuda Toolkit. You used to have to get a special license for it, and so it's becoming much more widely used.